ইলেকট্রোম্যাগনেটিক ইন্ডাকশন। ইলেকট্রোম্যাগনেটিক ইন্ডাকশনের একটা বেসিক আইডিয়া আছে, ক্লাস 10th লেভেলে করা আছে। এবার আজকে সেই আইডিয়াটাই একটু এক্সটেন্ড হবে using the concept of flux. So starting of the EMI takes place using the concept that if electricity in moving wire produces magnetism, এটা আমরা ফার্স্ট পার্টে শিখেছিলাম। So whenever there is a current carrying coil, so through which if the current is being flowing, it can produce a magnetic field, B তৈরি করতে পারে। So I can produce B, then opposite is also true. Opposite is also true means B can also produce I. That means a magnet moving near a wire could produce electricity. So that is the basic idea. So in the chapter magnetism, what is study that current can produce B. I can produce B value from I. That is called the magnetism. Now I want to ask whether the reverse is true or not. That means from B, whether I can get the I or not. Yes, I can get it. So ধর বললাম এখানে coil রয়েছে. So in this coil there is no batteries attached. So no current is being flowing. But once I insert a magnet inside this coil, so what we found that the bulb glows. Bulbটা glow করছে means there must be some kind of current is being flowing. So by movement of the magnet, something is happening inside the coil. Because of that, the current is start to flow, and because of that current, the bulb will glow. The bulbটা glow করছে ঠিকই, but that is not continuous. Once I insert the magnet, then glows, and then again it turns off as I move the magnet away from the loop. So there must be some kind of direction sense. So direction is not constant throughout. As I move in direction, if I say clockwise, current is being flowing. As I move out the magnet, the direction of the current is anti-clockwise. So direction is going to be changed. That means what I am trying to get is a kind of current which is changing its direction. That means it is an AC current. That means I am willing to produce the AC current. So electrical energy is converted to the mechanical work. Electrical energy converted to mechanical work. So for this setup, I need a battery. I need a battery which can produce electric energy, and now I want to convert into mechanical energy. Okay. So this form of device is known as DC generator or DC motor. So this is known as the DC motor, where I supply the electrical energy and I get the mechanical work. Reverse is that now the mechanical work is used to convert the electrical energy. That means I go inside the concept of which is known as the AC generator. So this is the concept of AC generator. So as an input, I am supplying the mechanical work. As an output, I want to get the electrical power. So this is called the AC generator. This is AC generator where the continuous AC current is flowing. এখানে একটা গ্যালোমিটার রাখা রয়েছে which shows the deflection in both the direction. So once the point is moving towards right and some other point it is moving towards left. That means it is oscillating current. That means a current which is known as AC current is being flowing. তাহলে in this system আমরা করছি কি, we are giving the mechanical work as input. এটা হচ্ছে input parameter, and as the output I am getting the electrical form of energy, and this setup is known as the AC generator or AC source. So there are different devices যেখানে আমরা এই কনসেপ্ট ইউজ করব। যেমন করে এইটা একটা হচ্ছে, বা হাইড্রোলিক টারবাইন যেখানে রয়েছে, where so once I rotate the rotor wheel, so that means the mechanical energy is being produced. Now this mechanical energy is transferred to the belt, to the smaller pulley. So now here is the generator. This is the AC generator, where the output is the electrical form of energy. So once we run the turbine, that means the mechanical energy is being produced, and that mechanical energy is converted to the electrical form of energy in a AC generator, from where I am getting the output current. Same is the windmill. In windmill also I am rotating the mill. That means the wind turbine is rotating. Because of that, the mechanical energy is being produced, and that mechanical energy is input given to the generator to produce the electric current. So these are the different applications where I want to get the electric current. Now, so entire thing starts from an experiment. So magnetism also starts from the Wested experiment. EMI is also starting from the experiment. So initially, there is an experiment that has been carried out. There is different setup of this experiment. Let us say I take a loop. And we place the loop in a magnetic field. Now, with time, let us say the B change. Magnetic field change. Either the B value can increase or B value can decrease. Both are possible. So once I change the magnetic field, what you observe that through this loop, some amount of current is being flowing. Okay. So keeping other parameters fixed. Now in the second experiment, what I am doing, I am changing the area. So gradually the radius of the loop is being either increased or decreased. That means once I change the radius of the loop, that means I am going to change the area. So either area can increase or decrease. And what I observe that again the current is being flowing. Okay. So direction of current, I will understand what is the direction of the current. So either I can increase the area or I can decrease the area. And when I change the B, what are the parameters that remain constant? That is the area is constant and theta is also constant. What is theta? Theta is the angle between the B vector and the A vector. Initially, if I say this is the cross direction magnetic field being applied, and if I rotate my finger along this direction, and I say the area is also cross, so that means the area vector and the B vector are fixed. They are not changing the direction. That means the theta is constant. Theta is the angle between the area vector and the B vector. In the second situation, I am only changing the area, keeping the other two parameters, that is B and theta are constant. B and theta are constant. Now in the third situation, so I rotate the wheel. I rotate the wheel in this direction. That means by not changing any other parameter. So only thing is that I give the rotation of the loop. So in this particular situation, A is constant, B is constant, and there is no change in theta value also. Theta is also not changing. And all are constant. So what you observe that no current is being flowing. I is 0. But once I rotate the loop in a vertical axis, that is in this vertical axis, once I rotate the loop, now the theta is going to change. Okay, keeping the value of B and A to be constant. At a time, I am only changing one parameter. So there are mostly three important parameters are there. One is the magnetic field, another is the area, and the third one is the angle between the B and A. In the fourth situation, I am rotating the loop. That means under this situation, only theta is changing. So what I observe that here also the current is being flowing. So I is not equal to 0. Okay. So after doing this kind of experiment, what I finally conclude that if B changes, then I flow. If area changes, then also I flow. If theta changes, then also I flow. Okay. So these are the observation of this experiment, that either B or A or theta can change. Okay. So combination of these three parameters is giving the magnetic flux. So I write the magnetic flux as phi B, that is equals to BA cos theta. Same logic goes for the electric flux, that is equals to phi E, that is equals to E A into cos theta. E is the electric field. Okay. So whenever there is a change in flux, okay, either I change the B value or A value or theta value, what I am going to change, I am going to change the flux parameter. So whenever I am changing the magnetic flux inside the loop, then there is a current in the loop. That is the answer for this situation. So what you observe initially I only change B or A or theta, but as a whole, what I am changing, that I am changing the magnetic flux. Okay. So magnetic flux is a scalar quantity. So what is the flux? Flux is a measure of the flow of magnetic field lines through an area. Same logic goes for the electric flux also, number of electric field lines crossing a particular area. Same logic, number of magnetic field lines crossing a particular area. So if I say through this coil, let us say I amount of current is being flowing. So this coil is generating some kind of magnetic field. Now these magnetic field lines are crossing through this area, let us say. Okay, so this is the area through which the magnetic field lines are crossing. If I say these are the number of field lines that crossing this area, if I count this number of field lines, so that gives an estimate of the magnetic flux. Okay. So magnetic flux is a measurement of this. So flux is the measure of the number of magnetic field lines crossing perpendicular to a given area. That means if I say B is along the horizontal direction and normal to this surface, area is measured. Area is always perpendicular to the surface. Okay, normal to the surface, 2D area. So the angle between the B vector and BA vector is theta. So for this situation, magnetic flux can be written as the phi B should be equal to. So for this elemental area, let us say the area is very small. So I can say d phi B, that should be equals to B dot dA vector. Okay, B dot dA vector. Or I can write B into dA cos theta. If I omit the dot product, so B dA cos theta. So ultimately what I am getting, that the total magnetic flux phi B, total magnetic flux phi B can be written as integration of B dot D. B dot dA vector. Okay, that gives the total magnetic flux. So if the magnetic field is constant, then I can write B to be taken out, simply B dot A. And if it is variable, then I should use this expression integration method. So every time, in order to calculate the magnetic flux, either I should go for this equation, or I can write B dot A vector when B is constant. When B vector is constant. That means when the loop is placed in an uniform magnetic field. When B is constant, uniform magnetic field. So then only phi remain constant. Phi equals to B into A. Otherwise, I should use this integration method whenever the B is a variable. So magnetic flux is a scalar quantity. Unit is Weber. Weber is the SI system of unit where use the notation for the flux is phi B. Okay. So 1 Weber equals to 1 Tesla into meter square. Tesla is the unit for the magnetic field and area is meter square. So 1 Weber equals to 1 Tesla into meter square. There is another CGS unit that is called the Maxwell. Not so much popular, but the unit is important because in some situations Maxwell unit is also being used. So 1 Maxwell equals to 10 to the power minus 8 Weber. Okay. এটা মাথায় রাখতে হবে যে 1 Maxwell equals to 10 to the power minus 8 Weber হয়. Okay. So for uniform magnetic field, as I have already said, B can be taken out of the integration. So ultimately B integration dA vector and dA is the total area. So B dot dA or B vector dot AB. When the magnetic field is constant. If the magnetic field is variable, then you should go for the calculation based on the integration. Now in this situation, so B vector and A vector both are parallel. That means theta equals to 0 degree. So once theta equals to 0 degree, so answer is B cos theta is BA. Okay. Now A vector can be in any direction, depending on the nature of the surface. So surface is now aligned and such that the A vector is making an angle 60 degree with the B vector. So in this situation, theta equals to 60 degree. So phi should be equals to BA cos 60 means BA by 2. BA by 2. If I take this is the area, according to you, area is in the opposite direction and B is in this direction. So now the angle between the B and A vector becomes 120 degree. So theta becomes 120 degree. So it should be minus BA by 2. Okay. So depending on the angle between the A vector and the B vector, the flux can be either positive or negative. Or it can be also 0. When the angle is 90 degree, then it becomes 0. So B is parallel to A. B is parallel to A means theta equals to 0 degree. So when theta equals to 0 degree, phi equals to B into A. If B is anti-parallel to A, so B is right side, A is on the left side. So theta is equals to 180 degree. And for this theta equals to 1 degree, phi should be equal to minus BA then. Okay. So either it can be positive number or it can be negative number. And if the angle is 90 degree, theta is equals to 90 degree. So for that situation, phi is equals to 0. So no magnetic field lines are crossing this area. No magnetic field lines are crossing the area. Why? Because the area is parallel to the B vector, or I can say area is direction of the area vector is parallel to perpendicular to the B vector. So flux is the measurement of the flow of magnetic field lines, and in this situation, no magnetic field lines are crossing the area. So that means the phi should be equal to 0. So ultimately, what is the objective of this chapter? So from the experimental observation, there are two basic objectives. Why? So first is the calculate of the direction of the magnet current. In which direction? So we understand that whenever the flux is changing, so current will flow. So first of all, we have to understand what is the direction of this current. And second part is the magnitude of this current. So there are two different laws which will satisfy these two answers. So first one is the Lenz law, then the Faraday's law. Okay. So start with the Lenz law. So Lenz law gives the idea about the direction in which the current is being flowed. Direction in which the current is being flowed. So in this situation, what is happening? Let us say I am inserting or moving the magnet towards a coil. Okay. So if I move the magnet towards the coil, as I move approaching, so from the north pole, the magnetic field lines are this coming out. So as the magnet is being moved towards the coil, so this red colored magnetic field lines will increase. Okay. And so what is loop is trying to do? Loop will try to produce a induced magnetic field in the opposite direction. Okay. Why? Because the red colored magnetic field is going to increase. So loop will try to produce an induced magnetic field that is along the B direction. So this blue color direction called the induced magnetic field. So in order to produce the induced magnetic field from the left hand side, if I see, as an observer, if I move on the left hand side, so for this left hand side observer, he sees that a left hand side or magnetic field is being generated towards the right hand side by the loop. So that means a current must flow inside this loop in a direction which is seen by the anti-clockwise direction for the left hand side of observer. Okay. So this is the clockwise direction. Why? Because if I rotate my finger along the clockwise direction from the left hand side, my thumb will be pointed towards right. Okay. So same logically, if I move away the magnet, that means north pole is moving away from the coil. That means in this direction, this red color magnetic field line is decreasing. So now again the loop will try to oppose this. Now in this situation, the induced magnetic field will be produced in this same direction. Okay. So in order to produce an inward induced magnetic field from the left hand side observer, if I curl my finger towards the anti-clockwise direction, now the left hand side observer will see a current that will flow in the anti-clockwise direction. So for this situation, anti-clockwise current will flow, and for this situation, clockwise current will flow. That means the direction of current is going to reverse. That gives the idea of the Lenz. Okay. So the statement is that whenever the magnetic field or flux is going to change, so that will produce the induced EMF. Okay, that will produce the induced effect. So induced EMF of current opposes the cause by which it is produced. What is the cause? Cause is the movement of this magnet. Once I try to move the magnet towards the coil, that is the cause. So if the magnet is moved towards the coil, that means along this direction, the magnetic field lines is going to increase. Yeah, this is the cause. So as a loop is trying to reduce this effect. So by producing an opposing nature. Now what is the opposing nature? Opposing nature is called the induced effect. So as an induced effect, the coil will try to produce a magnetic field in this opposite direction. So this is the induced effect. So this is generated by the coil. So out of nothing, the coil is producing the induced effect. But I know that in order to produce the magnetic field, the current must flow. So that means there must be some current is being flowing through the coil. Okay. So once I curl my finger along the direction, keeping the thumb toward the right, that means from the left hand side, what you observe that the current is being flowing in clockwise direction. Okay. Once I fold my finger in a clockwise direction, thumb will be pointed towards the right. That means now the galvanometer, so as I move magnet towards the coil, so you can observe that galvanometer deflection is towards right. That means clockwise deflection. Okay, as the magnet is approaching towards the coil, you can clearly see the galvanometer is deflected towards the clockwise direction. And as I am moving away from the coil, the galvanometer deflects in the opposite direction. That means the current is going to change the direction. That means whatever the current that I am getting out of this loop is basically the AC current. Why? Because it can change the direction. Okay. So far what we understand that whenever I am changing the magnetic field or by changing the flux, the induced effect is produced, and that effect is producing some kind of current. So if I say through a loop, some current is being flowing, that means some amount of induced EMF is generated. Okay. So that EMF formula is given by the Faraday. So what Faraday's law states that is equals to induced EMF. That means induced EMF is what? Induced EMF is nothing but the EMF produced due to the current. What is the current? So current is the induced current. Why current is being produced? Because of the induced magnetic field effect or induced flux. So because of that, the induced current is being produced. So induced current is being produced means that loop is acting as a battery. Why? Because without the battery, the current cannot flow. So what is the potential difference or the EMF of the battery? That gives the formula of the Faraday's law. So Faraday's law gives the rate of change of flux. d phi v dt is the rate of change of flux. So how the flux is being changed within the loop, that gives the idea of the induced EMF. Okay. Now from this, it is clear that if phi v is equals to constant, that means there is no change in the magnetic flux. No change in magnetic flux means epsilon induced is 0. Okay. That means whatever the flux that has been produced, that must be changed with time. If I can produce a time-varying magnetic flux, then only the induced EMF can be produced. Once I move the magnet towards the coil, that means the flux is changing with respect to time. So that means phi is a function of time. So that means we can do the differentiation to get the value of d phi dt. So that d phi dt number will give the induced EMF. Minus sign is giving the direction. Yeah, minus sign is basically satisfying the Lenz law. So this is called the Faraday's law. So why minus sign? Minus sign is nothing but to represent the opposing effect. Minus sign is representing the opposing effect. As the magnet is approaching, so loop is trying to produce the opposing effect. Loop is trying to produce the opposing effect. So what is the direction of the opposing effect? That gives the effect of negative sign. But in problem, every time I should use the mod value. Epsilon induced is how much? Basically mod of d phi. So that number will give the battery value. Okay. So once I calculate the epsilon induced, so through this loop, what is the current that is inflowing? That is equals to epsilon induced by R. What is R? R is the loop resistance. So that is the Ohm's law. So first we apply the Faraday's law to calculate the induced EMF. And once I apply the Faraday's law, that gives the induced EMF. Then we apply the Ohm's law to calculate the induced current. So that is the induced current. Okay. All the parameters over here are known as the induced. Why? Because these are being produced by some other effect. What is the other effect? At the movement of the some other thing. That may be the permanent magnet. That may be another current carrying coil. So it can produce the initially the magnetic field. So direction of the induced current, as I have already discussed, that it may be either clockwise or anti-clockwise. Since the flux is increasing, means as I am moving the magnet towards the coil, so can I say that this kind of magnetic field lines are increasing? So this is the increase in flux. Increase in flux. Because what is the flux? Flux is nothing but this B into area. This area. So through this area, the magnetic field lines are crossing, and this is the area that is constant. A is constant. I am not changing the area. So what is the flux? Flux is equals to simply B into A. So phi magnetic flux is equals to B into A. So why flux is changing? Because as I am approaching the permanent magnet towards the coil, the B value is increased. B is increasing. So since B is increasing, overall effect is the phi B will increase. So once the flux is increasing, magnetic field induced current will be opposing to that. Opposite to the existing magnetic field. So that means the coil will try to produce a induced magnetic field in this direction. Because increase in red colored line, so magnetic field that should be produced within the loop should be along the green color direction. So that is the B induced value. So that means depending on that, the direction of the current is clockwise, as seen from the left hand side. So for this observer, the current is the clockwise direction. But if I change the situation, when the flux is decreasing, so when the magnet is moving away from the coil, then the flux is decreasing, and because of that the current should be in the anti-clockwise direction. Okay. So that is the induced current is along the existing magnetic field. Why? Because in this situation, this B number is decreasing. This B number is basically the magnetic field produced by the permanent magnet. So B is decreasing. So opposing effect should be in the same direction. We should increase the B value. Okay. So this is the induced effect. Now, the induced effect is along the same direction in which the magnetic field is decreasing. So correspondingly, I should be in the anti-clockwise direction. So that B বাড়ালে তো clockwise বললাম, এই তো বললাম B যদি বাড়ে then the current is clockwise লিখে রেখেছি। Red colored magnetic field is increasing means that as I move the magnet, once I am moving the magnet towards the coil, so magnetic field lines coming from the permanent magnet starts from the north pole. আমরা north pole টাকে so this is the permanent magnet. So as I moving this north pole magnet towards the coil, so this is the coil. এই জায়গাটা coil কে রাখা রয়েছে। Okay. So as I am moving this magnet toward this, so magnetic field lines are from this north pole like this. Okay. So যখনই ম্যাগনেটটাকে আমরা কয়েলটার দিকে নিয়ে যাচ্ছি, that means along this direction B is increasing, না? So loop will try to produce the opposing effect. So opposing effect is what? Opposing effect is in this direction. So that is the induced magnetic field. Okay. So in order to produce a yellow colored magnetic field line through the coil, so I have to place my thumb towards right and fold the fingers of right hand. So as an observer, if I observe my finger from the left hand side of the loop, from the left hand side of the loop, what I will see? The current in this direction, the clockwise. So opposing effect is the yellow colored line. So that is called the opposing effect. So as I approach the parallel magnet towards the coil, that means the flux is increasing. So increasing flux is not the reason, is the cause. And what is the opposing effect? Opposing effect is the decrease of that. So in order to decrease the effect, so loop will automatically produce the induced effect. There is a magnetic field is automatically produced by the loop. Okay. So this is called the EMI. So electromagnetic induction means whenever I increase the effect of whenever I increase the effect of the external effect, that means by moving the magnet. So there may be another situation. So there may be is one loop, and there is another loop through some kind of current is being flowing. So if I approach this loop, that means for this second loop, the magnetic field line, let us say in this direction, so this is increasing. The same logic for the permanent magnet. Okay, so either the magnetic field can be produced by the permanent magnet or by a current carrying loop. So I have to increase the magnetic field or I have to decrease. So there are two possibilities. Either the flux can be increased or flux can be decreased. So depending on that, the opposing effect is either the flux is decreasing or flux is increasing. Now, another thing is that in this example, in earlier example, what I am changing only the B. Once I am moving the magnet towards the coil, the magnitude of B is increased or decreased. Without changing the B value, let us say now I fix the magnet. Once I fix the magnet, I know that whatever the magnetic field is there, that is from north pole to south pole, is in this direction. So this B is fixed. Now what I am doing, I am putting the loop inside this magnetic. Once I insert this loop inside this magnetic field line, gradually the area that encounters the B part will increase gradually. Initially no amount of area is crossing the magnetic field line. If no amount of area is crossing, let us say I keep a field cross. Okay. So there is a region inside is the cross magnetic field is existing. I put a loop which is outside this magnetic field. So that means at this situation phi is 0. As I insert this loop inside this magnetic field, gradually the area will increase. So as the area is increasing, so what I can say, the magnetic flux will also increase. So let us say after some point of time you see that this much of the area of the loop is inserted inside this magnetic field. So corresponding to this much area, the flux will be there. After some point of time, more amount of area will be increased. So as the loop goes on inside the magnetic field line, so area will increase. So that means the flux is going to increase. Okay. In what direction the flux? So flux has no direction. What I can say that as the area is approaching or area is inserting inside this, so gradually what you can say, the cross magnetic field line is increasing or the red color magnetic field lines are increasing. Okay. So loop will produce the opposing effect to oppose that. That means this is the direction of the induced current, induced magnetic field. Got it? As the loop is entered, whenever the loop is allowed to go inside this magnetic field line, so gradually the area will increase. That is the cross magnetic field, amount of cross magnetic field crossing through that area is going to increase. That means the loop will sense that as the cause. So it will produce the opposing effect. Opposing effect is to nullify the current effect. So what is the effect? Effect is the increase in red color field. Okay. So opposing effect should be decrease in that. So decrease in that means it has to produce a magnetic field in the opposite direction. Okay. So as an observer, let us say observer is standing over here. So for this observer, now towards the into the plane or towards the observer, the magnetic field lines are directed black color line. So for this observer, the magnetic electric current through this coil should be in the anti-clockwise direction. Okay, should be in the anti-clockwise direction. So you can clearly see that these dots are basically direction of the positive charge. Okay, so as I am moving inside this, so through this loop, once the loop is being entered in this direction, through this loop is the direction of current. Okay, so once I am leaving out of this loop, that means now the red current magnetic field lines is decreasing. So as the opposing effect, it has to produce the magnetic field in the same direction. So once the loop is moving out, then red colored magnetic field lines is gradually decreasing. So that means if the loop is completely entered now I am leaving out from this magnetic field. So gradually this area will decrease. So that means the cross magnetic field is going to decrease. That means red color magnetic field lines is going to decrease. Opposing effect is that it will produce the induced field in the same direction. Okay. So in order to produce an induced field in the blue color direction, again you have to rotate your thumb for the observer situated on the right hand part in the clockwise direction. So whenever the loop is coming out from this magnetic field line, the current will be in the clockwise direction. Okay. So in this situation, if the loop is coming out, so current will flow in the clockwise direction. That means again, I am getting two different directions. One is the anti-clockwise and the clockwise. Okay. So in the entire experiment, only thing that I am changing is the area pair. Okay. So by changing area, what I am ensuring that the flux is going to change. Okay. So either I can change the B or I can change the A. Okay. Now direction of the induced current. When I zero. If flux is constant, flux is not going to change, then there is no current. Why? Because epsilon is d phi dt. d phi dt যদি 0 হয়ে গিয়ে থাকে, that means phi is 0. That means epsilon is 0. Epsilon is 0 means I is also 0. So now in this situation, the magnetic field lines, dot magnetic field lines is decreasing. So decreasing dot. So opposing effect should be increasing dot. Nah. So dot magnetic field line is decreasing, so opposing effect should be increasing dot. So increasing dot value means the current should flow inside this loop in this direction, in this current direction. Okay. So there are four possibilities. So what are the possibilities? So first we understand what is the cause, and next we opposing effect. So first cause is that let us say increasing cross magnetic field lines are increased. So increasing cross magnetic field line, opposing effect is the decreasing cross magnetic field line. But decrease is not possible in opposite. Any effect cannot be decreased. So I cannot decrease this. So ideally, increasing cross should be the decreasing cross should be the opposing effect. But indirectly, what we can say that decreasing cross is not possible. Why? Because in opposing effect, no parameter can be decreased. I cannot decrease this cross magnetic. What I can do, I can increase the dot magnetic. So increasing dot is nothing but the decreasing cross. Increasing dot is nothing but the decreasing cross. So cross increment is nothing but the opposing effect, the dot increment. So if I decrease the cross, then the opposing effect is cross increase, and that is possible. Okay. So similarly, dot increase. So theoretically, it should be dot decrease, but again decrement is not possible. So what we do, we increase the cross, or finally decrease in dot. So decrease in dot should be increase in dot. Okay. So increase are possible. As the opposing effect, increase in parameter are possible, but decrease in parameter is not possible. So whenever I got the feeling that I have to decrease something, that means I have to think that other parameter has to be increased. So only two possible directions, either dot or cross. So in this situation, dot magnetic field lines are decreasing. So dot decreasing, again you have to increase the dot. That is the opposing effect. To increase in dot means you have to, along the same direction, the induced magnetic field has to be increased. Okay. That means you have to curl your finger, taking the thumb outward. Outward means dot. So once I put thumb outward and curl my finger, I see that the current inside the loop should be along this direction. That means this is the anti-clockwise direction. Okay. Similarly, there is a long current carrying wire. A long current carrying wire. So through that, I is increasing. So because of this I, the magnetic field line at the center of the loop is cross. Here the magnetic field line is cross. So increase in I means this cross magnetic field line is increased. So opposing effect is dot has to increase, cross has to decrease, but I cannot decrease the cross. That means dot has to be increased. So opposing effect is that dot has to increase. So dot has to increase means again the current has to flow in this direction. Okay. So every time you have to analyze the situation in such a way so that either I can go for increasing dot or decreasing cross. So depending on that, you have to select the proper direction. Now let us say decrease in direction in this current as seen by this observer. So once I go inside this loop, so this kind of magnetic field lines are increasing for this observer. So increase in blue color magnetic field line has to produce an opposing effect in this direction. So this should be the induced effect then. So as an observer, you want to see the yellow color magnetic field lines come together the induced magnetic field line. So place your thumb towards left and curl your finger from the observer point of view. The direction of the current should be in the anti-clockwise direction. Then you will see the current should flow in this anti-clockwise direction. Okay. Because for this type of problem, every time the position of the observer is important. Position of the observer is important. If nothing is specified, then the answer has to be given by position of the observer on the left hand side. So this is the default position. If the observer position is not properly defined, then assume the observer will be placed on the left hand side and then according to that take the direction. Okay. So that will give the answer. Similarly, once I move away from this, so for the south pole, these are the magnetic field lines. Magnetic field lines are going inside. So as I am moving away from the loop, that means this color magnetic field line, yellow color magnetic field lines are going to decrease. Okay, going to decrease. So as the opposing effect, I have to increase this. So this is the induced magnetic field line. Induced. So as an observer, again the current will flow in this direction, that is the anti-clockwise direction. Okay. You have to understand what is the reason or what is the cause and what is the opposite. Here the decrease in yellow color magnetic field line is the cause. And in order to counteract this, so I have to produce a separate induced magnetic field along the same direction. So once I produce the induced magnetic field in the same direction, then I am getting the idea of the induced current. Okay. So now find the flux to this way. Now, whenever you want to calculate the flux, so only consider area inside which the magnetic field is there. Okay. So the area of the loop is not important. What is important that in dA cos theta, that is the expression for the phi. Phi b. In expression of phi b equals to dA cos theta, what is A? A is the area inside which the magnetic field is there, not the loop area. So inside this, this area is basically your small a square. Okay. So phi should be equals to b into a square. Okay. Not pi r square. Every time the area should be the area inside which the magnetic field is there. Now here, only the half portion of the loop is encountered with the magnetic field line. So the area should be equal to then pi r square by 2. So b should be equals to, phi should be equals to b into pi r square by 2. Okay. So the area inside which the magnetic field is there, that is going to take part in the calculation of the field and calculation of flux. So phi should be dependent on the area of that area. Okay. So these are the some examples that you can solve it. Moving on to the next segment,